Hi, my name is Buck Woody. I'm an applied data scientist here on the Azure data team at Microsoft. Welcome to SQL Bits and to this session on machine learning, artificial intelligence, and deep learning for the technical professional. Well, there's quite a bit for us to cover in a short period of time, but don't worry, we'll show you lots of examples and other resources where you can find more information. Let's start out with data science. The term data science, kind of an umbrella term, and it's come to mean a lot of different things, but it's actually just a couple of big areas. The first is data analysis, and you're probably already familiar with this. You've done create, read, update, and delete, or CRUD operations. You've done that before. You may have even delved a little bit into business intelligence. An area that might be new to you, however, is data mining, where we bring statistics into the process to do some predictive work. In fact, data mining is the beginning of the artificial intelligence movement we see today. Now, not just the data analysis side, which you're probably already familiar with, but we begin to bring scientific rigor into this process. A standard process that we follow in science. Define the question, which is creating your hypothesis. I think this, I think that. Then you create a repeatable test, and then you publish your results. It doesn't map perfectly to this, but it does map fairly closely. A little different than what we've done in our standard extraction of data. We're going to begin to analyze it, and we're going to use some statistical and other math methods on top of that. Now, what is artificial intelligence then? If that's data science, if data science is sort of the area and the process, what is the technology of artificial intelligence? Well, artificial intelligence at its base is composed of machine learning. It's another umbrella term that has these things within it, and we'll cover all of them shortly here. But it also involves something called deep learning, and we'll talk more about that. Machine learning and deep learning are not the same thing. You'll often hear people call machine learning classical machine learning or classical machine learning techniques. And deep learning, you'll hear all kinds of things around neural networks and other terminology. And we'll tease out a lot of that for you today. Can't promise to teach you 4 years of math in an hour, but we'll get through a whole bunch of this as we go. Now, what's the progression here then? Where did all this come from? Well, back in my day, we had what was called good old-fashioned AI. Well, at least it's called that now. I'm not sure how I feel about that what I worked with is called old, but there you have it. This actually goes all the way back to the 1950s, and in our early days, we started seeing things like perceptrons and so on being developed, and this came up into the 70s, kind of when I started with this, with expert systems and other things, and then it moved into the 1980s. With data mining, we began to see a lot more of this process. Machine learning came in about mid-80s. That may surprise you that it's actually that old, but it became fairly popular in that area or that time frame. And then starting around 2010, we began to see techniques that sort of tried to model neurons in the brain, and we'll talk more about that. They didn't pull it off very well, I don't think, but we'll find out how that works. Well, now let's jump into artificial intelligence itself. So now we've covered the basics. Now let's get involved in some of the practicals, and we'll jump into some examples here in just a moment. Back in 1956, there was a summer research program at Dartmouth College, and they said human intelligence can be so precisely described that a machine can do it. In other words, we felt people were so predictable that they could be reduced to mathematical formulas. Well, I think we've proven the capacity of humans to be predictable is not true, but we can get fairly close. The development of this process came out of two sort of big ways. The first was the sort of symbolic systems. And what this meant was we used logic, if you're familiar with formal logic, like if A equals B, then B equals A, and so on, those kinds of things. Expert systems were what I used, which is where I defined a whole bunch of rules. And a doctor would say, well, does it hurt when you do this? And does it hurt when you do that? Okay, you've got this, and so on. Those were kind of expert systems. Someone once described them as a great many if-then-else statements, and they're not far off in that. And we also had things like evolutionary computing where, hey, if we could take an algorithm and it could change the next algorithm, what would that be like? And that was actually the germ of some of these things. Well, that then changed as we progressed into statistical models. We see inference, hidden Markov models, normative Bayesian decision theory, easy for me to say, on all these kinds of techniques that we saw. And this is exactly where we're at today, combining some of the best of the symbolic systems and some of the statistical methods that we have available to us today. With the power and the data that we have, we're able to create large systems that do artificial intelligence. The best place to start, by the way, is not to write artificial intelligence. Don't go write any. Just use it. It's already out there, and many places provide services that you simply call out to with an API, an application, or a programming interface, and you just call them and you get back an answer for your prediction. By the way, that's called a score. That's your first term whenever you say, hey, is this a dog or not? And it comes back and said, that's a dog. That's actually a score. It's predicting that it's a dog. And here's the first concept you need to think along with that. Everything in artificial intelligence and machine learning and deep learning is a guess. Everything is a probability. We think it's a dog and we have a certain confidence in that prediction. That's why it's called a score. Now, this means that artificial intelligence and so on is not very deterministic, and that feels, well, it doesn't feel satisfied to us. We want something that when we add 1 and 1, we get 2. Well, now we say 1 and 1, it's more than likely 2, which feels interesting. However, Microsoft, for example, has many cognitive services, we call them, that you can use. Everything from vision to search and anything in between. You can see some of these are in a different color, the little orange color there. And what that means is those can be customized. And not only are they an API you can simply call, but you can actually customize them and send some different things in and train them on different things depending on what they are. Lots of things here. More than likely, you're covered by just using the pre-built AI. That's the industry term, and our term is cognitive services. So we'll show an example now of how that works. Let's talk a little bit more about how you can actually perform artificial intelligence in code, in SQL, and other places. Let's take a look. We'll begin in Azure Data Studio. The reason I'm using this particular tool is it can run Jupyter, with a Y, Jupyter, notebooks. And these are simply web pages, really, that have two kinds of things. They have text and they have code that you can run. And they do it all there in the main part of the screen. It's very easy to see, very easy to work with. If you're new to that, go look that up. The code that you run depends on the kernel that you pick. And Azure Data Studio provides several. We're just going to do everything in Python today, but there's lots of kernels you could use. And localhost is where it will run. Inside, you can do this in SQL, you can do it in Spark, you can do it in lots of places. We're just going to run the Python I have installed locally. All right. Let's take a look at our first example here, which is just cognitive services. We're just going to go out and use pre-built AI. Now, I've got some steps for you to take, and the first thing you'll need to do is you'll need to go create a resource. There's a free version of this. I'll let you read up on that. Just follow the links. These notebooks will be made available to you. Let me show you where the page is there. Here's how you create a service, and then once you create your service, you'll need your keys, and these are the way that you can talk to the service. So with those two pieces of information, you have everything you need. So this explains a little bit of what's going to happen. Let's assume we've got a feed somewhere for social media, and what we want to do is we want to tell if people like us or they don't like us in our company. We want to get something called sentiment analysis, and this is a form of artificial intelligence that will extract text, read the words, and say, I think they like you, or they don't like you very much, and so on. So here's a particular flow that you could use. We're going to use a much simplified one. We're simply going to read something and then print it back out. That's the way we're going to do it. So to do that in Python, don't worry about Python if you don't know it. There are places where you can go to learn more. We want requests. This allows us to talk to essentially a REST, R-E-S-T, representational state transfer, HTTP. If you're using a web page, that's REST. So we're going to make a REST call, and then we're going to get the pretty printer to get the JSON in a way that we can sort of read it. And then all I'm going to do is just print the libraries are loaded. Now I've run all these cells already and then strip my keys out for two reasons. One for time, and the other is I don't want to give you my keys. I know you'd love to have that. When you do the step up here about creating your Azure account and getting the key, those values will be given to you in the web page that it links to, and you put your subscription key. It'll give you an endpoint that you use that's specific to you, and then you'll get your keys and so on. All right, the next thing we're going to do is we're just going to go grab text analytics. As we mentioned, there's lots of services we can use. We're going to get text analytics. Your information will go sort of right here. I think you have the flow at this point, and that gives you your API call. What are we going to ask for? Images, language, video, what, right? So that's going to do that. So now what we're going to do is we're going to read our document. Now this could be inside your SQL Server. It could be out on the web. It could be somewhere else. We're going to create one. We're just going to invent one on our own, and we're going to do this. The first thing I want to do is I want to find out what language is this. When I'm sent a language, now you as a human can look at this, and if you know a little bit about things, you could probably tell this is English. You might know if something's in Spanish. If you speak Spanish, you probably would guess, okay, that must be Spanish. But if you're not familiar with an ideographic, a picture type language like Korean or Japanese or Chinese, you might not know what number 3 is. Maybe you do. I'm an American, so I don't speak very many languages. I speak more than some Americans, but not very many languages for me. So anyway, we don't know what that last one is. And the first thing we need to do if we're going to get sentiment, we need to figure out which language we're dealing with. So I've just created a JSON document. It's a key value pair. Here's the key. The ID is 1, and then the value text is just the words. All right, you get the general idea here. We've read some data from somewhere. This could be in your database now. Keep in mind, you could do all kinds of things by selecting things out, running the Python that I'm about to show you, and then popping it out to the web. Then what I'm going to do is I'm going to say, hey, send me that. Send the key, send the document, and so on, and it'll print the JSON that it returns. So I'm going to send it JSON over an API call, and it's going to return JSON over the IP call. And the things that it returns, by the way, are detected languages, because that's what I asked for. And it gives back these fields. It gives me the ISO name, the international name, and then, you know, the EN, all that kind of stuff, ES and all that kind of stuff. And then it gives me the friendly name, which is English, and then how well it thinks that really is that. And it's pretty confident in these. It knows this one's English, it knows this one is Spanish, and it knows that one's Chinese. And any errors that it would have gotten, it would present that as a collection. Now you can tear the JSON that you get back and do something with it, like print on the screen, this user is speaking Chinese or Spanish or English. Very fascinating stuff here, and it's done in tenths of seconds. So as I mentioned, don't build machine learning, don't build deep learning, just go use it. And you can do this today. So I've given you lots of resources here in this notebook for you to go learn far more, but this is a quick and simple example of artificial intelligence and simply using it. That's fascinating stuff, and we've got lots more to go, but you can get started there, and I've got a full school for you for free, aischool.microsoft.com, and you can run out there and find out far more about artificial intelligence than you probably ever wanted to know, and more about how you can use it. Now let's talk about machine learning. So we've seen sort of the process of data science, and we've seen the families and where it came from and the history. And we've even seen an example of using pre-built AI. Well, how is that working sort of under the covers? What is the math and the science behind those? Let's take a peek at how all that works. Well, it's very simple, actually. Let me give you the formal definition of machine learning. It's very simple. A computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance at task T as measured by P improves with experience E. hopefully you got all that and made some notes. Maybe we should simplify that with a quick example. Let's simplify it a bit. So let's take a look at some things here. You can see that I've got some attributes. You can think of them as columns or whatever you'd like to call them about an object, and it's going to be a certain image, and you're going to look at that image and you're going to give it some tests. You're going to say, does it have an open top? True or false? Does it have a closed bottom? True or false? Can it hold liquid? True or false? And is it hand-sized? True or false? So I'll show you an object in a moment. These things are called features. The columns are simply called features, and the score, the result, is called a label. Is it right or not? So we know this in advance. We have some data that we know it in advance. So we have some images we've done here, and you can see that the first one's true, and the second one's true, and the third one's true. The fourth one rather, is my cat Tina, and Tina is not in fact a cup. She doesn't have an open top or a closed bottom. Trust me, she does not hold liquid, and she was hand-sized, but she's not anymore. She's a fairly chunky cat, so she's no longer. So she's not a cup. We kind of understand that. So we can now create a model. We'll just use if statements, and I'm oversimplifying here, but if it's an open top and a closed bottom and holds liquid and hand size, it's true. And we could do all kinds of things around that, but we can now get rid of the data. We no longer need that data. We just need that model. You were able to look at this, evaluate all these things, and you now have a formula like Excel in your head that says all these things. When you see a cup, you go, that in fact is in fact a cup. You can do that. So let's take that model, get rid of the data, and let's take a look at a new object and let's apply it. Open top, true. Closed bottom, true. Holds liquid, true. Hand size, true. Now the interesting thing is this one's a different color and in a different orientation than our other tests that we ran or our training data. This is a test data. Now we happen to know, the computer happens to know whether this is a cup or not, but we're going to see if our model is very good. And so it takes a look and it says, you know, it meets the model, but it's blue and it's slightly rounded, and some of them are and some of them are not. One is rounded, but it's brown, it's faced. I'm about 90% certain. And that's our score. And that's how this works. The models work kind of this way all the time. Now, there are different models. This is far oversimplified. And there are different ways to do the math around this and create. And there's lots and lots of features, one label, and then lots and lots and lots and lots of data. And we show it over. By the way, this is the way a child learns. Cup, cup, cup. And then, you know, the child picks up something else and the cup, and no, not a cup, cup. And so they get the trues and the falses in their head the same way a machine does. Well, I think we talked a little bit about that now. I mentioned about those families. Let's talk about what those are. The first is how much or how many. There are algorithms that are called regression algorithms, and they're like a trend line, and they map out X's and Y's very well, and sometimes even Z's, and they can tell you how much or how many something is projected to be. If I was a day older than yesterday, more than likely I'll be a day older today. I'm pretty sure about that. And in 10 years, I'll be 10 years older, and I'm pretty sure about that. That's a regression algorithm. Another one might be, is it odd? Now, these are hard to find. These are called anomaly detection methods because there are so few false positives, or excuse me, true positives. And what I mean by that is if you have a lot of bank records, most of them are not fraud, but 1 or 2.5% might be fraud. So it takes a lot of math to weed out all the positives so we don't get all these trues in there and it confuses the model. So this is an is it odd or an anomaly family. The next one is a classification family, and these are actually a series of trues and falses. You've seen those coin banks back in the day where you would put a coin in and it would roll down the slots, and when it hit the slot that was the right size, it would fall in. Well, that's exactly what these are. And there are multi-class, like it's a bird or a tool, or there's single class, which is it's a bird or it's not a bird, it's a bike, it's not a bike, it's a tool, it's not a tool, and so on. Another family is which action, and this is reinforcement learning. I've got the thing clipping the red wire and the green wire. I don't know, in the movies they always show clipping the red wire. Maybe if I was a bad guy, I would always make all the wires red. I don't know. At any rate, the reinforcement learning is kind of how your automatic vacuum works. If you've got one of those little Roomba things that bumps around, it's actually developing an algorithm of that's a wall, that's not a wall, and it reinforces, it makes a mistake, and then it corrects its own mistake. And there's a family of algorithms in that. Then there's one that's kind of unusual in that it is not supervised. What does that mean? Well, supervised learning means we know some truths and falses in our data. We have the answers ahead of time to train it. But in clustering, we don't know truths or false. We just throw some people down, we throw some data down, we throw some movies down, and we say group those together as closely as you can. And what they'll do is cluster things. And you've probably seen this. If you like this movie, you'll probably like this movie. That's done with a clustering algorithm, and that's on unsupervised data. So these are our primary families. These are our 5 primary families, and there's lots of algorithms in each. Don't worry, there's a way to check which one you should use when. We'll go through that. Now that we know the families, where can we use them? What languages do we have available? Well, the ones on the columns here are the primary languages you'll see. R and Python keep switching places as the favorite. R has a lot more statistical libraries and is a purpose-built language, and it also has something called Shiny, odd name, but it's a really nice interface that allows you to visualize these things quickly. Think Power BI, but for R, even though you can use R in Power BI. Python is a more general purpose language, and you'll see it show up. There's a little bit of both. You couldn't go wrong learning both of these. And basically then they load in libraries to be leveraged. So these are things other people have written, and you can just say, hey, do a clustering algorithm using this library, and it will do that for you. SQL is actually not a machine learning language, but it's quite often used for data prep, and so you'll see that used quite a bit. Java can be used for machine learning. They actually have a few libraries for that, but I see it very rarely in the industry, although it works very well for n-grams and other kinds of data prep also. Almost all of these are included within SQL Server and the data platform here at Microsoft. So you've got availability on those. You know, we've talked about this enough. Let's go see one in action. Using Azure Data Studio again in another Jupyter notebook, this time still using Python. We'll use that throughout for everything. We're going to take a look at a machine learning algorithm, and we're going to put it in the guise of a team data science process. Now, in many cases, people do everything in one seat. There's one person doing all the work. But in today's world, as things have become more evolved and we're more mature in these areas, it's usually a team that's involved. And we've got a specific process. You can see that at aka.ms/TDSP here, and you can learn about the team data science process. Breaks it down into very nice phases, and I explain what each of these phases is. So what are we going to do? Well, we've got Orange Telecom, the Orange Telecom company here, which is in France, and it's one of the largest operators of mobile. And basically, they're interested in doing something called churn prediction. They want to know if a customer they have is about to go to a different carrier because they're unhappy or something's wrong with the service or whatever it happens to be. So they want to predict so they can maybe do some preemptive stuff. They call them and say, hey, we got a new phone model out. We notice yours is older. You're having some issues. Would you like a new one? And so on. So the first thing we do is we set up a bunch of libraries that we need. One, it's interesting, I might point out here, is Pickle. Pickle gives me the ability to save everything we're doing into a binary object. And then anything that can run Python can sort of open that up and replay it. So once I've created my model, I can now port it somewhere and use it, even as SQL Server or SQL Server Edge. The next one that's kind of interesting is Pandas, and Pandas is the general purpose Python data library. So it gives you all kinds of ways to work with something called a data frame, which is typical or similar to a table inside SQL Server. And then we go get some machine learning models, I get some things to deal with libraries and so on, and this is fairly common. Once again, I've run this notebook ahead of time just to save us some time, even though it's fairly quick. Now what I'm going to do is I'm going to go out and grab a telco churn training sample. I've just got one out there. Don't know if this is going to stay, so if you try to run this, you may want to find another example for that data. But at any rate, I then just look at the data, and this is the data acquisition understanding. I go find out about the data. I look for missing values. I look for statistical displays. I just kind of look at the data and see what's there. Now that I've kind of seen what I have available, and remember, we're talking about those features and labels, right? So you got all kind of features here: age, income, and education, homeowner, marital status. And then we've got our label, which is, did they churn or did they not churn? Now remember, we're going to train on data we know, then we can show it. Once it knows what a cup is, we can show it a cup that it's never seen and say, is that a cup, right? Is this person going to churn? So we need a lot of data to do the training, and we need no data to score the model, if that makes sense. Okay. So we have our labels, we have our features, and now we're going to start our models. First thing we do is we get rid of all the nulls. Now in Python, this is called an NA. And you don't always want to just get rid of the nulls. Sometimes you want to put something in there. Sometimes you don't want to put something in there. Sometimes there's even libraries and algorithms that can figure out what to put in there. And it all depends, and this is very statistical oriented. You want to know your stats well. Just throwing a 0 in there could be a huge problem, or it may be exactly what you need. In this case, I need that exactly. Then I'm going to get rid of my duplicates because that's going to screw things up for me as well. And I don't need year and month. It's kind of immaterial, doesn't do anything about that. And then I do something called one-hot encoding. Basically what this does is it takes a value like red, green, blue, orange, and it makes columns out of those and says red, yes, that would mean then green is no, and blue is no, and orange is no, right? That's the way that kind of works, kind of like a pivot table, if you will. It works that together. And then I put all this back together. I set some things to be categorical. Once again, this has to do with stats. And I train my model. I show it all kinds of stuff. And then I hold out a certain amount of data to see how well it did. And then that's called the holdout data or the test data. And now that I've trained it, I give it a test just like you would a child in school to see if they've been paying attention to the algebra class. And I take a look. And the particular model I'm going to use here, or algorithm I should say, that I'm going to use here, is the decision tree classifier. And you can go learn more about that, but you already know what a classifier does. And we're looking here to see whether someone is going to churn or is not. That's a classifier. So we see how that works. The standard call for this is to fit the training data to the target data and so on. And then we say, what do we get? And it goes and does all this work. And it does two of those. I actually did a decision tree, and then I also did a naive Bayes here. And again, you can go learn what a naive Bayes here does. And this is common. This is the experiment part. And I see who does better. And it looks like with a small amount of data and a very quick rundown here that I get a little better accuracy from decision trees than I do from naive Bayes. So I would now run that model again with just the naive Bayes, create the model, and I would pickle that out, and then it will create a file because I told it to use model pickle. And now I can use Python and the pickle library to open that back up, send the data in. It's going to expect these things about the person. And once it gets those things, it will spit back out, I think they're going to churn, or I don't think they're going to churn. And I'm about this sure. And it's going to tell you how that works. Once again, that's called a score. Now, when we're all done, you can see kind of what we do. We get a web service ready to go here. And I'm just going to get my web service that's ready to accept these columns and then uses the model to predict it out. And then let's just send something in here. I've sent it in just to kind of figure out what's going on for that particular client. 1 is churn and 0 is no churn. This particular user is not going to churn. So that's the way the model works. Again, much to read, lots of things at the top of this page, but there's an example of a machine learning model that is used to create the artificial intelligence prepackaged stuff that you've seen. Well, more to learn, right? So don't worry, I've got a full course for you here. The Data Science Essentials course out on edX.org is a great place for you to go learn more about machine learning inside these different algorithms and families that you've just seen. Well, now let's take a look at the most complex part. Now, I cannot simplify the math too far for you, but I will try to make these concepts as simple as I can. Then we'll dive into a fairly complicated example, and I'll point in that to a lot more courses that you can go to. There's a lot of reading here, but the concepts are something I think you can grasp fairly quickly. Well, let's talk about what deep learning is. The first thing you need to understand is layers. Now, when we think about a brain works in a way where you have little neurons in your head, and it's got a couple of things that we care about, actually three. One is called an axon, and the other is called a dendrite, and the other is called a synapse. Let me explain what those are. First of all, we have the neuron itself, which has some processing work it can do, for lack of a better term. By the way, when we say we model the brain, we're not even close to the brain. Deep learning and machine learning and artificial intelligence is to the brain as a pencil is to a computer. Just so we understand each other, that this is not, we're just modeling it after a neuron. Neurons are hideously complex, and they have billions of interactions, and there are billions of them. Even the deepest learning models are only in the thousands, so they're not even approximating. But here's the way that works. Neuron has some information in it. The axon's a long tail with little feet at the end, and the dendrites are on the other side of the neuron, and they've got little feet that stick out. The axons of one neuron talk to the dendrites. Think of a bunch of these things laid next to each other, talking together, but they don't actually touch. There's a little space in between them, and there's some neurochemicals that go between them. They shoot across like little bullets, and that area is called the synapse, and that's where the data transfer happens. All right, with that understanding, let's take a quick peek at how this might work. First of all, I've got this represented as just a couple of layers here for you to see. The ones we care about are the input layer and the output layer. And then in the middle, there are these things called hidden layers. Just ignore those for the moment. So we take in some inputs and we begin to see, let's say with our eyes. Vision is a great place for deep learning, as is voice. And as we take these things in, they create a number. They come in with a number. And that number gets a little formula in that first one. And then the next dot there represents perhaps another connection. The next dot is another connection. And they all do something. Like, you know how your eyes see edges and then colors and then shades of gray and so on. And that's the beginning of you recognizing your friend Jane that's coming towards you and so on. All right. So those inputs come in, those things hit, they get a number assigned to them, and then they are sent to other neurons, if you will, another layer. And there's usually lots of these layers, and it's all math in there. And there's little triggers that happen with this math called an activation function that will kick it up and then say, that is this. Okay, that's red, that's an edge, that's gray, and so on. And these things come in, and at the very end out there, there are some results that happen. And when you put those results together, you get an answer. Simple, right? Actually, the math of it is a little different. There's also things called weights and biases and activation functions, and I'm going to have to let you go out and read about those to see how those kind of work. This is kind of a zoom in on one of those dots is the way that works. And there's usually a smoothing function, a sigmoid, or some other mathematical function that sets whether that activation function is going to be triggered up or down. You could think back in the modem days. Do you guys remember modems where we take the modular demodulation, where we take an analog signal and we turn it into digital? Very similar. That's the way it works. For those of you who don't know what a modem is, just go get on your Insta, TikTok, or whatever it is. All right. Here's the way a real network sort of looks like this. If you take a look, here's the input layer coming in. This is a fairly complex one of a picture of things. And then we have maybe one layer does edges and maybe one does combination of edges. One does sharpness, one does is it an eye, and so on. And then we've trained it to have these object models, and it recognizes that as a face, and potentially a specific person's face. Facial recognition works in this way. Even these hidden layers, there would be probably thousands of these in a complex sort of model. So what is deep learning sort of good at? Well, it's good at complex predictions and classifications. So a machine learning model, if I were to give it this picture and I were to show it more pictures like this, just like this, it could probably guess this is that same picture or not. That's all it can really do, or it could cluster it, or it could predict it, and so on. That's about all it can do. But on a trip to Africa I took not long ago down to Johannesburg and then Cape Town, we were driving around and I was looking in the field, and they said, look at all the wild dogs. And I'm looking out the window. I'm like, what wild dogs? And they said, right there. And there it is. There's a wild dog. And if you look to the left, you'll see there's a bunch of wild dogs. Like 14 we counted in that picture. They're all over the place, but they're very well camouflaged. You know, isn't nature wonderful? So they blend in with the shadows perfectly. Well, this no way a machine learning model could pull out that picture from the others. It just couldn't happen. So deep learning can go closer to this. Now, this would be even a challenge for deep learning, but this deep learning is well suited to these kinds of tasks. Well, we've talked enough about that. Let me go show you some things, and I'm going to hand wave a little bit here and get you to some math for you to take a look, and we're going to talk about some of the actual mechanics to make this work. Okay, we're to the deep learning example now. I'm going to have to hand wave a lot here because there's a lot of math and there's a lot of concepts. I'll give you some resources, though, to sort that out. The thing we want to do here is we'd like to do some text recognition. Let me pop over to a web page. This is called an MNIST. Don't get worried about that. It's basically a symbol set that the post office used years and years ago, which is a real useful thing for handwriting recognition. They need to recognize handwriting on envelopes. Now, you do that as a matter of course. Your brain has been trained over the years to recognize your language, and you can recognize these no problem. But I think you can see the 8s and the 7s, the 1s and the 5s. Oh my gosh, they're dramatically different. For a computer, it either is something or isn't something, and in fact, it's expecting the ASCII code to 00175 or whatever it is for the number 8 or 7. That's what it expects, and if it's not that, it doesn't know what to do with this stuff. So we need a way to figure out the handwriting. It was one of the first applications of sort of these deep learning layers. So I'll set up some libraries here, and I'm going to set up my sigmoid function. Now, you recall that I talked about sort of the activation functions and so on, and that's what I'm doing here, and I'm just grabbing a numerical library to work with, and I've run these ahead of time to save us a moment or two. Now, we're going to create a class, a neural network class, and we're going to keep adding to it, and then at the end, we'll use it. So we're going to use an artificial neural network, an ANN. These are obviously abbreviated a lot of times just a neural network, but there are other kinds. There are adversarial networks and things that go backwards and forwards, RNNs and GANs and all these other networks. We're just going to stick with these here. This is my first hand waving I have to do, but I've got a link for you in the notebook for learning more about neural networks. And then also about those weights and biases that sort of, I've flipped the way that this layers are. They were on their left last time when we saw in the example. Now they're coming down. And these weights and biases are the things that will give it a little tweak on the way in and make it decide. Your brain does this all the time. Is that a dog or a wolf? Your brain goes, oh, pretty thin, pointed ears. I think that's a wolf. So you bias towards these kinds of things a lot. All right, first thing I do is I just set up a class for our ANN. I get my weights and my outputs and so on. So then we need to add feed forward. Now, feed forward just means it's going to start at one layer and move straight through. There are also other ways of sort of re-wrapping yourself around and doing these multiple times. We're going to stay fairly simple, and we just do a 2-layer network here. Remember these layers right here? We're just going to do 2 of the green dots, 2 levels of those. And again, you can read far more about multi-layer ANNs and feed-forward neural networks here if you want to read more about those. Now, This is quite possibly the most difficult thing to understand, is the backpropagation, the loss, the gradient descent, and the chain rules. Basically, all of those things involve this. They involve trying to make it as accurate as possible. That's literally what they're trying to do. They're just trying to make it accurate. And so when you see something and it's far off and you're like, is that a truck? And then it gets a little closer. Oh, no, it's an SUV. What kind of SUV is that? Your brain is like figuring out you're wrong, and it's making changes. This works in everything except apparently politics. But when you find out you're wrong, you make a change. That's what we're doing here. And it involves math. That's the loss function. And then it uses backpropagation to get the gradient descent, and it does that with a chain rule. And I've got all kinds of things about that here. I even have a fun little video you can read to or watch to learn more about the chain rule. So I set all that up. We're still building our network. That's what I'm doing here. And again, much more to learn. And then now we want to predict the letter. So here's our numbers. We want to predict letters, not numbers. So let's do this. I've zoomed way in on some handwriting, and you can tell me, what letter do you think that is? Well, it's an L, right? And that one looks like an L. That one does not look like an L. I don't know what that is. I don't know what that is either. And this one looks like an L. Yeah, it looks like an L as well. So to do our work, we need to turn these handwriting things into numbers. And to do that, let's start off with the way that you've probably worked with computers before, with just pixels, boxes. So let's take some boxes, and let me turn image 0 and 1 and 2 and 3 and 4. Let me just put some boxes over those. Hopefully you're okay with that. Now we're getting closer to being able to do numbers with those, right? All right. So we have 5 images here, and we've got some boxes are darkened and some are not, zeros and ones. Getting closer. So now what we'll do, stick with me, let me show you what we did here. I took this one right here, and I sort of unrolled it. I took the line, I'm pointing at the screen. I took the line here and tacked it onto there, and I took the line here and I tacked it onto there, and I made this. Do you see? 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8, 9, 7, 8, 9. You see that? And that means then that this one's a 0. There it is. This one's a 1. This one's a 0, 0, 1, 1, 0, 0, 0. Ta-da! All right. So we have now these things which we're going to call our features. We'll call these blocks is dark or is not dark a feature. And I've done that with each of these. There's 1, 1, 1, 1, 1, 1, 0, that would be 1, 1, 0, and so on. You get the general idea. And I just did all that, and I made myself a tensor is what this is. So I've made myself a little vector or an array of things to come in, and now I'm just going to send it, but I've added something. You can see that the numbers that I ended up with are not the numbers that are in this little thing. What this is I happen to know, remember this is a supervised set because I have the label for the model to train on. I can train it because I've told it that's an L. That's not an L. That's not an L. That's an L. That's an L. So it now knows, by the way, here's the full set of data. And I've said, hey, your first data set includes these, and that's just the features, and then your last one is your labels. So I've set up my X and Y's here, and you can see features and labels. All right, we're ready to get started. We can feed this thing in now. Here we go. So I'm going to create my neural network. I've done that. It's got a memory location, and now I just need to send it the test that I want to run, or the training I want it to run. So I'm going to say, you know what? For I in range 1500, right? Do this a whole bunch of times. Then feed forward, add the back propagation, and from range 0 to 5, do this. The 2-layer neural network is, and then I go do some math, and % sure that the image is an L. So this is my training phase, and it runs through and it tries to do as many of these as it can, and it says, I'm 99% sure that the first one is an L. I'm 99% sure the second one is an L. I'm not super sure that the third one is an L, and I'm not sure the fourth one is an L, and I'm pretty sure the fifth one is an L. So once I've done that, I can persist that model back out again now that it's been trained, and then reuse it. There are many kinds of these, and there are many functions, and there are many pieces of math that can be changed here. This is probably the simplest one you'll ever see, but With these others, when they're run multiple times, those are called, another term is epoch. You'll see them run multiple times. Those are called epochs. And the concern here with deep networks, these deep learning networks, is that you can overtrain them. You can actually train them so many times that they begin to memorize. And that's not learning, that's memorization. They would only recognize that L. Which could be a problem. So you don't want to overtrain your model. How do you know when you do that? You run experiments, and then you try it and you test it and you run experiments. Again, all machine learning, all AI is just a guess. Okay, there's a great video you're going to learn from in just a moment. I'll show you that resource right now. Is your mind melted yet? Listen, I work with this stuff every day and it's still something new to learn. There's a great overview here on this YouTube link. I'll give you a minute and let you, I didn't make it short, I apologize. After all that brain work, I've made you memorize a bunch of numbers here. This is an excellent overview of how deep learning really works. Okay, where can we do all this? How do we do all this? What do we do it on? Well, you've already seen how you can call out to cognitive services. And you've also seen how I've been doing things inside Python. What you may not be aware of is that SQL Server in most of its flavors, and there's a chart where you can figure out which has it. But on the virtual machine, your local installations of SQL Server, a managed instance and other places might have this, but you've got the ability to run machine learning services, MLS, inside SQL Server or alongside SQL Server technically. But it allows you to do everything we've done today. Everything we've done today could be done inside SQL Server. And that could be done on-prem, it could be done at the edge, it could be done in the cloud, or all of the above. You might train on large sets of data in the cloud and then deploy the scoring mechanism locally, select data out of your SQL Server to be compared, and then come back. It's a fascinating world, what you can do. The point is, your SQL family, as we call it now, has lots of places for you to do machine learning and artificial intelligence. Well, I hope this has been useful. It's certainly been a whirlwind tour, and there's certainly much more to learn, but you can do it. And now you have a good vocabulary, and you'll be a hit at parties when you explain to someone how AI, machine learning, and deep learning works.